Here we are, and we're ready for the hypergeometric distribution, ready for class here. And we'd gotten through partway through section 3.5, and I'd like to finish that today and finish chapter 3 for that matter. And it looks like we'll have enough time to get our foot in the door on the beginning of chapter 4, continuous probability distributions. And without a doubt, the most important one is the bell curve, the normal distribution, and we'll have extra time to spend on that. The rest of 4 is kind of a warm-up to that, but let's first of all finish up chapter 3, some miscellaneous distributions, for lack of a better word. We'd gotten to the hypergeometric distribution, and sometimes the trials are not independent. They're kind of dependent on each other, and they're without replacement from a finite population. Hypergeometric does a pretty good job of summarizing that. So we'd left off with kind of a summary of the expected value, and what they would like to do is the variance. And then I kind of left off with the fact that if P is just M over N, remembering the notation, M is the number of successes in the entire group, and N is the total in the entire group before you take the sample, which involves, taking the little n, etc. So we put the P as M over N, and so E of X is, expected value of X is just N times P. That is the mean as before. And the variance of X, which is the standard deviation before the square root, is what I call NPQ. And right now they have a finite population correction factor. And some books don't use it in certain conditions, but this book will always seize the opportunity to do that. So let's take a look at some examples. Primarily, I'd like to explain the examples to you with just enough theory to get you by. Let me see if I can maximize the screen a little bit. Maybe not. Okay, anyway, we refer back to the animal tagging example that we talked about before. And so we had 25 total, and 5 were of interest. That was M equals 5. And so 5 of them were tagged, and then 10 will be the sample. So we'd like to find out what X could be, and we'll just find out what the expected value of X and the variance of X would be. And the mu from this group, considering we had 5 out of 25, is 20%. Yeah, so there we are, 0.2. And then we have N and our new sample size, the little n, of course, compared to the population size of capital N. And so our expected value clearly is 2. That's pretty easy to do. And I'd say rather intuitive as well. But the variance, especially the variance, and more like the standard deviation, a little less so. And so they go through and plug in all the numbers. The correction factor gives us 15 out of 20. N and P were just like before, 10 and 0.2. And then what I call Q, 1 minus P, is 0.8. And that works out to be exactly 1. And then the standard deviation is a piece of cake because that's 1 also. But if we had ignored the correction factor, and if it had been done with replacement, it would have been a 1.6. Well, that's not that important right now. Once in a while, I'm not sure if we'll see this, but sometimes N isn't actually known, but we have all the other things in place. We observe the value X out of the little sample size N, and we also know what capital M would be, so that's the total of interest, but we don't happen to know what the total population would be. So they put a kind of a hat on it. It's called N hat, which means we're kind of estimating it, and it'll be an estimate for that. So we get 250 after plugging all the numbers in. N was 100, 100 times little n, 40, that's 4,000, divided by 16, x, and so that ratio would be 250. That would maintain the same proportion. It's just like a proportionality situation. So if you had N is 40, X is 16 out of 40, that works out to be 40%, then 100 would be 40% of 250. So that goes all the way back to beginning algebra, but let's not go there. Most books don't bother to do the N, but to solve for N, but that's fine. And they talk about a little bit of theory here as the hypergeometric approaches the binomial distribution for this P, or N over N, being small. And they're approximately equal provided P is not too close to either 0 or 1, somewhere in the middle. And anyway, they go through a little bit of that. Let's go finally to the negative binomial distribution, the second part of 3.5. So this is similar to what we've done, except now we're looking for a total of R successes and had been observed where r is a specific positive integer. And specifically, we're looking at the number of failures that precede the rth success. So that's what x would be. And the number of successes is fixed. The number of trials is random. Like how many free throws would it take you to get 2 free throws, not just 1? Or maybe even more. Would it be a lot? Would it be just 2 because you're really good at it, et cetera, et cetera. So those are things that we can observe with a negative binomial. And we just have, I guess, the one example here, but they do talk a little bit about something that's going on here. NB is their abbreviation for negative binomial. Every book is a little different on that. So the number of failures that precedes the rth success is the random variable x. And so let's take a look at 7 for x and 3 for r, and then p, well, we'll just let p be kind of flexible. So we're looking for 7 failures occur before the 3rd success. So that's kind of a lower p, I would imagine, odds are. So in other words, for this to happen, the 10th trial must be that s. There must be exactly 2 s's amongst the first 9 trials. They're kind of reasoning it out before they give you the formula, which is a good way to go. But some people are just formula oriented, but it's nice to see why it works. And so looking for 2 successes amongst the first 9, there is 9C2 or 9 choose 2. Then following the binomial formula, really, we have p squared and then q to the 7th. That would be 9 minus 2. These exponents must total up to the total, which in this case is n. So we would have, in this case, yeah. So anyway, we go ahead and consolidate it, and then we multiply it out and get another p in there and get p cubed. So we'd have to multiply by the p in order to get to the final answer. It gives us a total of 10 events. So yes, we have that trial. 10th trial must be an S. That accounts for that last p there. Then here is a formula. Of course, you do get a formula sheet. These are becoming miscellaneous formulas. It's certainly not 100% I would give you one of these on a test, but it's certainly a non-zero chance. Let's put it that way. So this is the way of setting up the NCR or choose column, and then we've got P to the R and Q to the X. So that could be done that way. Here's the example for this part of the section. A pediatrician wishes to recruit 5 couples, each of which is expecting their first child. They're to participate in a new natural childbirth regimen. So now we're looking for little p being the probability a randomly selected couple agrees to participate. And they're going to assume right now that p is 0.2, 20%. What's the probability that 15 couples must be asked before 5 are found who agree to participate? That is, with S being agreeing to participate, what's the probability we get 10 failures before the 5th S? So one could even say like 10 tails for your 5th head if you're flipping coins. But not in this case. R is 5, P is 0.2, and X is 10. That's the number of failures before we get to the 5th success. And yes, we subtract the 1 away. The formula is instructing us to do that before we kind of apply that extra success there. So 14 choose 4, in other words 14C4, which is a viable number you can get on any calculator. 0.2 to the 5th power for R equal 5, and then 0.8, the number of failures, X. And 0.8, of course, is 1 minus 0.2. I call it Q. I'll still call it Q because most books do that nowadays. This book doesn't want to do that too often. So that was only 3%. That's not too likely. That's kind of good news to get all the way up to 15. That would be kind of bad. It might be pushing a deadline of some kind. That may not be the best. But then, probably more importantly, what's probably that at most 10 would be observed. So you might, get less than that. It might be quite a bit less than that. So they set it up in a general way and let X be open-ended from 0, in other words, getting 5 successes in a row, all the way up to the worst case, which we just did, with 10 failures before we get our mandatory 5th success. So they put it into the summation notation. There's 11 things that have to be summed up here. And I don't believe they have a negative binomial table here. So when we do all of that, you only get to 16%. So 16% chance that it would be less than 10. Okay, so in the special case where R equals 1, in other words, the first success is what we're looking for. Like, how many free throws does it take for you to get your first free throw made? This is a special case and turns it out to be the geometric distribution. Q to the xp, or simply pq to the x is the way most books call it. Your book has to be different. So y is equal to the number of trials, x plus 1, and they go through, and anyway, that's just sort of a minor topic, just in case you do have r equals 1. It just sort of collapses into a special other distribution. There's at least 30 distributions that I've seen, and I know there are a lot more than that. And so here's the expected value of x, and then the setup for the standard deviation, the variance. So we could say all of that, and I would just say E of x is RQ over P, and the standard deviation of x would be the square root of RQ divided by P, because square root of P squared will just be called P here. And so they go through a couple of other theoretical scenarios. And that's all fine and dandy. But meanwhile, let's go over to the Poisson probability distribution. This one gets an entire section on its own, so it's just a little bit more important. Problems involving volume or area in some cases, or even time, with really no upper limit. In other words, x can tend towards infinity, such as number of visitors in an office hour in an hour. Could be 0, could be 1, 2, 3. Really no limit depending on how popular the office hour is. I guess the limit would be the total number of students the teacher probably has. But anyway, we don't really assign a limit, although it becomes close to 0 as you get up the ladder that high. But this is another distribution that we can use. And the Poisson distribution had to do with the, I guess it was the 1800s, and the Prussians were involved in a war, and they actually counted the number of people being injured by horse kicks, being kicked by horses, and that's where the distribution came from. Kind of weird, but probability came from casinos, and Poisson came from the Prussian army and all. And of course, there's the Guinness beer distribution. We'll talk about that another time. But a lot of these have stories behind them. So e to the minus mu times mu to the x divided by x factorial. They seem to come out of nowhere, but they actually derive it here in this book. Most books don't do that. Of course, you know what E is, 2.7, etc. And Poisson distribution spreads probability over all non-negative integers, an infinite number of probabilities. So possibilities starting at 0 without limit. There may be a practical limit, but we're not going to assign it. So it's not obvious that this looks real. But they decide to use some calculus. I don't know how much calculus you've had. I know you're all at least enrolled in it. But they say that the Maclaurin series, check your calculus book, says that e to the mu, or e to any variable really, would be equal to 1 plus mu, and then mu squared over 2 factorial, mu cubed over 3 factorial, etc. And that's where this part of the formula comes from. However, we'd like to set this equal to 1. So we have to divide by e to the mu, because that is almost for sure not equal to 1. And so we put e to the minus mu up in the numerator. I suppose you could put it downstairs with e to the positive mu. It's just most books, I've never seen it done that way. But anyway, this accounts for that extra term there. And then notice our summation goes from 0 to infinity. So we're not going to actually say that. So we basically just boil it down to this part of it. And that is our probability distribution for values of x that fit the bill from 0 on up. Integers only, of course. And we do have a Poisson table in case you'd like to look at it. These are cumulative distribution functions and will not list individual values except at 0. And I believe most software packages will include this. So I think the TI does. This one is more important than the prior two distributions, so that is certainly something to keep an eye on. Okay, so this example here says x is the number of traps, defects of a certain kind, in a particular type of metal oxide semiconductor transistor, and it's supposed to have a Poisson distribution with mu equals 2. Okay, so the probability there's exactly 3 traps according to the formula, and the formula is back here. So we'd have e to the minus 2, because that's what the mu is. Then we go to mu again, so back-to-back mu's, but 2 is raised to the 3rd power. So it's kind of a race between the exponent and the factorial. But here's what happens. The factorial wins. Use L'Hopital's rule if you want. Well, anyway, we have this value works out to be 18%. And also informatively, you could get this from the table, I suppose, but x being less than or equal to 3, they go through and they find 0, and they find 1, and they find 2, and they find 3. I actually worked this out just a few minutes ago just to double check on them. And yeah, they get all those values, and 1 and 2 are actually the peak. It's just they work out to cancel out pretty well. 2 to the first over 1 and 2 squared over 2 factorial is the same number. So we really just boil it down to a version of e to the minus 2 power, which is 0.135, and we double it, and then we multiply by 4/3. Well, I'll let you work that out if you'd like. And so the latter cumulative probability could be found in the table. I'm not going to dig that up and show it to you this time. But if you need to find just the individual value, 0.180, you just subtract two cumulative probabilities. Capital F means you're looking at the cumulative distribution function. The one at 3 and the one at 2, subtract the 3 on back, 3 down to 0 minus 2 down to 0 gives you exactly 3. In other words, x equals 0, 1, 2, and 3. This one equals 0, 1, and 2. The difference is just x equals 3, and there it is, 18%. You can find it by table or by formula. I recommend that you've used the formula at least a few times. The table, I don't know how relevant that would be, but the formula can be quite handy, especially if you're not totally sure of your calculator. So the book goes into a little bit of theory. That's why I'm kind of gliding through these subjects today a little bit. They do say that if n gets very large and p gets close to 0, then the binomial distribution approximates the Poisson distribution. In fact, there even is an approximation that is used for this. And they say that you can use an approximation for large numbers if n is greater than 50 and the NP, which would be like the mean, is less than 5. So they show how this example will unfold. A publisher of books takes great pains to ensure its books are free of typographical errors. I've never found a book that was entirely free of typos. Even 10th editions sometimes will have silly mistakes. But anyway, we have a 600-page novel. And what's the probability that one of the novels will have exactly one page with errors? And then at most 3 pages, the second follow-up question. So let's go ahead and figure out what we would have with n equals 600 pages and probability very low. I didn't point that out, but half of 1%, 1 chance in 200, 0.005. And so when you multiply those together, 600 over 200 is exactly 3. That is the mean. But now we're looking for a relatively clean book with only one mistake. What's that probability? It'll be about 15%. But why would that be? Well, instead of using the binomial formula by itself, which might be tedious and it might not even, sometimes your calculator can't even do it because the numbers are so extreme. I've been known to find numbers like that you would have to actually remember the approximation. I'm not saying I'll do it, but this is why the approximations are there, because sometimes you get like 60,000 and a 0.0001. You might not be able to cram that into your calculator. There are limits sometimes. This is why they have the approximations. So anyway, it's about the same as p with 1 versus 3 with a Poisson. So 3 is the mean, and 1 is what we're interested in. X is 1, and mu is 3. So they plug it in. E to the minus mu, e to the minus 3, and then mu to the 1, that's pretty easy. And then divide by 1, that's pretty easy too. This is just 3 times, 3 over e to the 3rd power. Anyway, you can find that on your calculator. And they say that if you actually did this officially, it would be very close. Really, to 3 decimal places, it's the same. And if you needed to find less than or equal to 3, you may take that number for 1 and add it to x equals 0, x equals 2, x equals 3. Get them all together. I'm not going to show the work on that. And find that it's close to 65%. So if you're looking for a book that has 3 pages or less with errors, you've got a pretty good shot at it, about 2/3 chance that would occur. And here's a little bit of theory. It's mildly interesting, I suppose, but I'm not going to make a big deal out of it. Here we have mu equals 3 back here, and then that's what we had, mu equals 3, along with 3 binomial distributions with also np equals 3. And we take a look at n equals 30, p.1, n equals 100, p.03, and n equals 300 with 0.01. All of those have np's equal to 3. And they're all a little bit different. Poisson is the prize we're trying to get at. And about the only reason we need to use this approximation is if we reach the limit on our calculator or package that we're using. And sometimes it would have to depend on approximations. I'm not sure how often that would occur, but this is why they're there. And also because of theory as well. They like to show theory here. So they kind of go up the ladder. For example, if x equals 0, the Poisson distribution gives it right around 5%, but so do all of these. However, if you're down to only 30 in your sample, now it's down to about 4%, 4.2%. Then it's about 4.8%, 4.9%, and that would round to 5.0%. So it turns out that Poisson is higher than any of these approximations for the first two x's, 0 and 1. And then it's actually lower than the approximations for the next four of them, that is from x equals 2 through x equals 5. You can take a closer look if you feel like it. Then it goes back to being higher from 6 through 10. And they even have a graph as they belabor this point quite a lot. This is difficult to read. I just can't seem to expand it today. There we go. Okay, so binomial n equals 30. Okay, there's the 0. You can see that very barely. And then you've got binomial n equals 100 is the x. So it drives it up a little higher, a little bit down in the middle, a little bit higher on the ends. And the Poisson is simply the line, the actual value of the line. So they're all kind of coming to a close merging, but we want to see how good the approximation is, and then we see that it's not quite the same. In some cases it's very good, in other cases it's not so good. So that's the idea there. So they make a big deal out of that, which is okay for a little bit of trivia, I guess. Okay, let's continue. And let's see, we have the mean and the variance of the Poisson distribution. This is probably a little bit more practical to us. And the funny thing is, they picked mu for a reason. These limits are np equals mu, and npq, the variance, also equals mu. So this is a time I actually pay attention to the variance, because in this rare, probably unique situation where the mean and the variance are the same, who would have known? And then, of course, more practically, though, the standard deviation is the square root of mu. So, yeah. And anyway, that's the idea. And so from the prior example about the traps, we found that the mu is equal to 2. So that means the variance would equal 2, and the standard deviation would equal the square root of the 2, 1.414. You've seen the square root of 2 a few times. Okay, then we'll go to a slightly longer section called the Poisson process. They extend it to time. And other books don't really worry about the notation. They just say it's time. But your book decides to add more notation. I guess that makes it a little more official. And I'll cover part of this, but volume and time seem to be helpful items for the Poisson. So yes, a very important application of this distribution arises in connection with the occurrence of event of some type over time with no real limit. Events of interest may be visits to a particular website, pulses of some sort recorded by a counter, email messages sent to a particular address, accidents in an industrial facility, cosmic ray showers observed by astronomers in a particular observatory. Yeah, okay. And then they go through a little bit of, deltas and all. And yes, that's all quite entertaining, and we'll just sort of glide past that a little bit. And they've really just used, well, let's see this. The first assumption says that alpha must be greater than 0. And for a short interval of time, the probability of a single event occurring is proportional to the length of time interval. So the longer time you let something have the opportunity to occur, you would have a higher probability, or a higher average, you could say. And really, they've just taken the Poisson probability and substituted for mu. They put in alpha times t. So t is a component, and alpha is just a proportionality constant. So seems a trifle unnecessary to me, but it is a way of incorporating t into the formula, and that's a good thing. But otherwise, it's the same formula. And also, they've decided to let x equal k. So that's a minor thing. The occurrence of events over time is called a Poisson process, and the parameter alpha specifies the rate for the process. So suppose pulses arrive at a counter at an average rate of 6 per minute. So alpha is 6, a standard unit of time. To find the probability in a half-minute interval, 30 seconds, at least one pulse is received. Note that the number of pulses in the interval is Poisson distribution, with alpha t being 6, that's the proportionality constant, times the time interval, 1/2. So we get an average of 3 over this particular time interval. It's rate per minute. So x will be the number of pulses received in the 30-second interval, where x will be, well, let's see, x being greater than 1. Let's see what we would do with that. We could ask for the probability that x is larger than 1. I don't see that they've done that yet, but okay, let's just go ahead and ask that, x greater than 1. So to do that, we don't want to go for x equals 1, 2, 3, 4, ... infinity. Instead, let's just use this complementary idea where we edit out the part we don't want and say we'll subtract that from the grand total 100%, and we will have our answer by kind of backing into it literally. And just by default, we'll get all the other numbers all the way up to infinity. So we just throw out the only one we don't want from the total, which of course is 1. And we put that number in. It's 0.05 to 3 decimal places. In fact, it was back here. It was on the prior table. We just saw it. And so that gives you 95% with no need to add up an infinite number of formula calculations. That would be ridiculous. So at least that's an interesting idea that you could take advantage of. So instead of using time, you could observe events that occur over volumes or areas. And you might select on a map a certain region R in a forest, go to that region and count the number of trees. Each tree would represent an event occurring at a particular point in space. And so using assumptions, it can be shown that the number of events has a Poisson distribution with the alpha times A of R, but A is the area of R. So, and you can do the same with volume as well in certain other areas. Okay, so that seems to be it for chapter 3, and I'm going to jump ahead to chapter 4. So let's see if we can do that. And they have a little bit of introduction. Just to recap what we did in chapter 3 briefly. Chapter 3 concentrated on the development of probability distributions for discrete random variables. But now we're going to go to the second general type, many applied problems, and that will be for continuous random variables and their probability distributions, with the main goal of looking at the normal distribution, the king of all the distributions. And so I have basic definitions in these first couple of sections, and then we study the normal random variable and distribution, unquestionably the most important and useful in probability and statistics. And then we look at a few others, but chapter 4.3, section 4.3 will be a long one. So that may take more than one lecture, but it's worth it because so many things depend on it. You just can't live without it. Throughout most of the rest of the class, it's just that important. And then we have 4.6. I believe I'm going to be skipping 4.6 due to lack of time. Okay, let's go to as much as we can get through in 4.1. I don't think this has a lot of examples, so this might go a little bit quicker. And I'm not so apt to spend as much time on the theory. And by the way, that other book that we have may be a little bit more to the point, and I do reserve the right to actually use it for some of the lectures coming up. Anyway, the discrete random variable was one whose possible values constituted either a finite set or maybe could be listed in an infinite sequence, such as we have a first element, a second element, etc. But we could talk about ones that are not discrete. And continuous is where possible values comprise either a single interval or on the number line for some a less than b, or any number between a and b is possible value, of course, and then we could union a bunch of disjoint integrals. I'm going to stop that there. And probability of x equals c is equal to 0. If in the study, in this example of ecology of a lake, we make depth measurements, x could equal the depth, of which location is continuous random variable, a is the minimum depth, b is the maximum depth. Very easy example. Here's another one. Chemical compound is randomly selected, the pH is determined, and x is a continuous RV because anywhere between 0 and 14 is possible, but maybe we could carve up a subinterval and say that x is between 5.5 and 6.5, but we still have continuousness. So in 4.3, we represent the amount of time a randomly selected customer spends waiting for a haircut before the haircut commences. You might think it's continuous, but there are some customers, maybe the first of the day, that have no wait at all. or maybe other dead times of the day where nobody happens to be there. And so you would have probability of time weight being 0 being actually more than 0. So you have maybe 10% of them just walk right in. But this one turns out to be a mix of discrete and continuous. So it's conditional on no chairs being empty, though. The waiting time would be continuous. Well, you can skim through that a little bit more if you'd like. Okay, so we're talking about sometimes discrete is very finely subdivided, but continuous models approximate real-world situations very well, and so continuous mathematics is much easier a lot of the time to work with, and we'll do that as much as we possibly can. Okay, make sure my disk doesn't fill up on me. As we go to this part of the 4.1, probability distributions for continuous variables. This just gets into something that I've shown many times in a PowerPoint that I wrote up a few years ago, where we have, well, they say here's the lake. The depth of a lake is x. And m is the maximum, and so the maximum depth in meters. And so any number between 0 and m is a possible value of x. And you can measure the depth to the nearest meter, discretizing it, they say. Possible values are non-negative integers less than or equal to m. And so we just talk about integers only. And the resulting discrete distribution can be pictured by using a probability histogram such as this. Rather coarse, but as we know, for a probability distribution, we have to have all the probabilities add up to 1, whether it's to the nearest meter or maybe nearest, I don't know, centimeter. That would be not realistic, maybe nearest quarter meter or something like that. And as we get finer and finer and finer, this starts to approximate a smooth curve. So either way, the probability underneath any of these must add up to 1. And of course, the third one is the best one, especially if we could find a formula for it. Without that, you may be better off using the histogram. But anyway, they talk a little bit about how those are developed, and you can certainly skim through that. And we can go between just A and B, certain areas that we're interested in. And it would be the area of the smooth curve between A and B, which may not add up to 1 anymore because this may be a subset. And this is what they mean by that. Say we take that lake and we just go from one part to the next and find out what that probability would be. And this is looking a little bit like calculus, I would say. We have a function f of x, which sometimes we can name quite easily and sometimes we can't. But a is less than b, of course, less than or equal to b, and so we're going to go the integral from a to b of f of x dx in a general sense. The graph here is referred to as the density curve. So there you are. And then we talk about a rather basic distribution. In fact, this is one of the easiest distributions of all. It just comes out of left field. But for it to be a legitimate probability density distribution function, it must satisfy the two conditions. It must be greater than or equal to 0 for all x. We only care about what's above the line or maybe sitting on the x-axis. And then the integral from whatever limits you can think of, minus infinity to infinity, must equal the area under the entire graph of f of x, which has to equal 1. Now, calculus doesn't have areas always equal to 1, but in statistics, we always do, at least for starters. So in this example, they talk about the direction of an imperfection with respect to a reference line. Goes along, and you can read some of that. The line connecting the valve stem to the center point and the angle measured in degrees, 360 degrees. Turns out that we round it to the nearest degree, let's say, or just to the next degree. However, we do have 1 over 360 for each possible degree, and 360 is not included. By the time you get there, they just call it 0 again. And anything else doesn't make any sense, so we just zero it out. That's a formality. And so we talk about the probability distribution between 90 and 180 degrees, and that is 1/4 because it's covered 1/4 of the area. And it's easy to do that. 180 over 360, because this just integrates to x, and that's pretty simple with a constant of 360ths. And yeah, 180 over 90, it gives you 90 over 360. You should subtract the two, the difference of the two gives you 1/4. And the picture even shows it more clearly. If it stopped here, we're taking like the second fourth out of the entire distribution. And yes, we're clearly taking a fourth. That's just like one segment of a circle, for example. And so if we take within 90 degrees, we could even add on another possibility as well and make it 0.50. That would be this block over here, be within 90 degrees of the reference line, but that's getting a little bit too specific for my taste, I guess. So whenever A is less than B is between 0 and 360, it really just depends on the width B over B minus A of the interval, because our height is always the same. That kind of edges things out. So we have a uniform distribution here when it stays between A and B and becomes rectangular, and that's what it is. We just have a rectangle. We're slicing bread. The way I look at it, we take a big quarter-sized bread, a big slice of the bread, and that's our probability. B minus A. B would be 180, and A would be 90, for example, and that's 1 over B minus A. Okay, let's see. We go through a few other little things here. Wanted to get to the example. Yeah, this one is interesting because it says when you have discrete numbers, I think we may have mentioned this before, then you can find positive probabilities. And in a discrete case, we see how the little blobs of probability of various magnitudes are distributed along the measurement angle, like those histograms we saw. But in a continuous case, probability density is smeared, in this case in a continuous fashion, and when it's smeared uniformly, like in a complete rectangle, we have a uniform PDF, very special case, which is just meant to be kind of an introductory case. It's a very simple one compared to others. And they're saying this boils down to the area of a line is 0. And so the probability that we have an area over one particular value would be like integrating from C to C, or even tossing an epsilon here with the limit of epsilon going to 0. You're still going to get it to go to 0. And even probably a better idea is when you slice a rod of some kind, or maybe just a pretzel stick or something like that. Now you just cut it, and you don't take anything out. You don't have any area to speak of. So they mentioned that over here, yeah. So the rod is sliced at points A and B. This segment is removed. That's the amount of mass removed. But if it's just simply sliced at a point C, you just break it into 2 pieces, no mass is removed. It's 0. So that takes a little thinking of it first. Oh, and by the way, because of that, we do not care with the probabilities here for continuous distributions, whether you use less than or equal to or not. Makes absolutely no difference at all. This is just a little bit easier, so that's what I tend to use. I certainly wouldn't want to mix the message because that looks a little bit misleading, perhaps. But it turns out all 4 of these are exactly the same for a continuous distribution. And some people have a little trouble getting used to that, but I'm sure you will not have any trouble with that. In this example, which looks like the last example of the day, so we'll be winding things up pretty soon, time headway in traffic flow is the elapsed time between the time that one car finishes passing a fixed point, say a gas station or something, and the instant that the next car behind it passes that point. So how much time has elapsed? This is a heavy flow model, so there's not much time. I suppose if you're out in the middle of the desert at 3 in the morning, it may be quite a long time, but here it is meant to be during a period of heavy flow. They do mention that right here. So following PDF of x is suggested by a certain reference there. And so it's 0.15 e to the minus 0.15 times x minus 0.5. For x being greater than or equal to 0.5 of a second, they forgot to put the units in right now, but if it's not quite that long, then they just call it 0. We're not going to mess with the small values. Okay, so no density associated with times less than 0.5, and headway density decreases rapidly. They even have a picture coming up here in just a moment, so let me see if I can squeeze this back. And this is the picture we're aiming towards. So what we're going to do is to look at the graph of f of x given. Of course, no density associated with times less than 0.5, so we trim that off. And so we put in the values between 0.5 and infinity, and we go through and verify that it does work out to equal 1. Kind of surprising perhaps, but I did some of the math on this earlier today and verified that it actually worked out. This is minus 0.15 times minus 0.5 does give you e to the 0.075, which is a constant, and 0.15 of course is a constant, so those are conveniently pulled away from the integral, and then you can then try to integrate this and verify. And they do use a little bit of algebra. Here it is. They kind of crammed it into the book. They actually expanded it out on the URL. That's nice. So e to the minus kx dx, is equal to 1 over k. So one can plug in the numbers and verify that that actually does work out. So we do find that that is true, and when we integrate that, we find that everything just totally cancels out. The 0.15, the 1 over 0.15, e to the 0.075, and the e to the negative 0.075 all conveniently cancels out, gives us 1. Here is the density curve. And then they say, what about the headway time would be at most 5 seconds? Well, that's going to be just about 50-50. So all those that go between, the minimum, half a second, and all the way up to 5, is pretty much the halfway mark of the distribution. So yeah, so if you're just interested in 5 or less, then the math will show to be 49%. So we can briefly take a look at this. Once again, they pulled the constant out, and now they're just integrating from 0.5 to 5. And so they go ahead and do that. They just go ahead and use that little formula they gave us to refresh our memories, the 1 over k, etc. I just tried to point up there. And so then we can then substitute 5 and substitute 0.5 and get the fact that you can subtract these two numbers out and get and multiply by a number that's very close to 1, surprisingly, this number here, 1.078, and you do get 0.491. So that's how that works. So they do talk a little bit about making, for a continuous distribution, cannot usually be derived using simple probabilistic arguments. Well, that's okay. But we must make a judicious choice of a PDF based on prior knowledge and available data. Fortunately, there are some general families of PDFs that have been found to be sensible candidates for the wide variety of experimental situations. So anyway, that's nice to know. But there we have the beginnings of the continuous distributions. We're aiming towards the normal distribution. And next time we're going to go into a cumulative distribution function. There's a thing called ogive that we might mention, and various other things. A little bit of theory coming up. But 4.3 is the big one. And I'm going to try to at least get our foot in the door on that in the next live lecture, which is Wednesday. Wednesday, I guess that would be the, let's see, today's Friday, that'd be the 10th. Wednesday the 10th would be the next live lecture, which would start at 4.2, and I expect to at least get partway into 4.3. I don't think I'm going to cover 4.2 in great detail. Our bread is buttered in 4.3. That's a huge, huge section, without doubt the most popular and most important section in the entire book. So I don't say that all the time, but in this case it's obvious. So don't miss it. Okay, so we'll let you go. I should have the test ready pretty soon. Anyway, have a nice few days there. And I guess it's going to be raining by the time you watch this probably. So stay safe, and we'll talk to you guys later.